right? When plotted the isotopic signatures in a diagram, the mantle reservoirs are falling in a way like this, right? So where can you see the depleted mantle? You can see the depleted mantle here. Okay, depleted mantle here. So if you take the depleted mantle, what can you how can you characterize it in terms of neodymium and strontium isotopes? Just by looking at its position, can one tell me how can we place the isotopic composition there? I mean, how can you characterize the isotopic composition of the depleted mantle? What do you think? In a diagram like this, your depleted mantle is plotted like somewhere here. What does it imply? How do you compare strontium and neodymium isotopes there? You are having high neodymium value here, isn't it? This is the increasing direction, right? So for the depleted mantle, you have a high neodymium value, isn't it?
Yeah.
What about the strontium?
Strontium values are low.
Yeah, strontium values are low. Strontium values are low. So the characteristic of the depleted mantle in terms of a neodymium strontium isotopic diagram means depleted mantle is having high neodymium isotopes while having low strontium isotopes. That is one characteristic of depleted mantle. So if you are getting a sample with, for example, an unknown sample from somewhere, and if you analyze isotopic compositions, neodymium and strontium isotopic compositions, and if you are ending up with the high value of neodymium and low value of strontium, then definitely you know that this sample is coming from depleted mantle. That is that's the way how we characterize our samples geochemically. Okay, so we have to look into the isotopic composition. We have to check the isotopic composition where this sample is plotted, right? For example, if your isotopic value is plotting somewhere here, for example, right? Suppose you have some value here. There, what do you think? That means your second sample is plotting somewhere here, right? Number 2. I'm putting number 2 here. This is number 1. High strontium value and low neodymium value, isn't it? So high strontium value and low neodymium value means it cannot be a mantle sample. Okay, so it's not belonging to a mantle sample. It's characterized by a different isotopic composition. So that's how we characterize the samples. So anyway, for the depleted mantle, you know now that the isotopic composition should be high in neodymium, right? That means the epsilon neodymium value also should be high, right? So higher epsilon neodymium value must be there for the sample. Actually, these values are present day isotopic compositions. Remember, present day isotopic compositions. Okay, present day isotopic compositions. If you are getting present day isotopic composition as a high number for a depleted for a sample, so that indicates it's a depleted mantle, because you know these isotopic compositions are evolving, varying, changing, right? Right. Now, in the first slide, what I want to emphasize you is the first, I have just put here the BSE as a reservoir. What is BSE? Bulk silicate earth. Bulk silicate earth means actually the composition of the earth at the time of its formation, right? That's a bulk silicate earth. So, you know, this bulk means, you know, silicate earth. What is silicate earth? Can anybody tell me about silicate earth if you have heard of it? Because in your first years, you may have just learn some of these concepts. Bulk, it's a whole, it's a complete set. That means the total silicate earth. Bulk silicate earth means the total silicate earth. So what is the silicate earth? What do you mean by the silicate earth?
Is that the primitive earth?
Yes, that's correct. It's a primitive earth. That's another term. That's primitive earth. So if you take the earth, right? If you take the earth and at the very beginning, that means the primordial earth. We call the primordial earth, right? Primordial earth. Okay. Primordial earth was not differentiated. I think you know that, right? What is differentiation? Chemical differentiation. The earth's chemical differentiation means what? That happened to the early earth. Yes, anyone? Any guess? What do you mean by earth's differentiation? If I say that it started at 4.5 billion years ago, that is the origin of the earth, time of the origin, and at least a few hundreds of million years, this differentiation took place. First 100 years, one stage of differentiation completed, and then until I think 3.5 billion years time, the second stage of differentiation continued. So what is that? Earth's differentiation, you should know that this term. If I say that primordial Earth was not a differentiated planet, it was not a differentiated planet, but our present day planet is a differentiated planet. What do you mean by that?
So the present day Earth has layers that are, we know that crust, mantle, and core after the differentiation process.
Yes, that's very good. Yeah, that's it. That's what I wanted to get from you. Differentiation means that the Earth's changing of the planet into different layers, right? Depending on different properties, right? So originally, what happened? At the first stage, that's what I mentioned about the 100 million years time after the formation of the Earth, 4.5 billion, 55 billion years time. From there, 100 million years time it took, and it separated. What was the separation of the first layer? What was the first separation?
Oh.
Yes, the core was formed. Okay, so that is the first differentiation. So what do we have in the core? What are the materials we have in the core?
Ferrous and nickel.
Yeah, iron and nickel. Okay, so those are completely metals, right? Iron and nickel. There is no silicate portion there. Okay, so the entire part of the earth was the silicate part. Understand? So in the core, what we have is iron and nickel. There are those are non-silicates. So entire part of the other layer which is available at that time was the silicate portion. So that is what we call the bulk silicate earth, right? Because there has been no crust formed at that time, right? So there was no crust at that time. What was there? Entirely a silicate layer, right? That is what you call the bulk silicate earth. So that is the primordial time. That is the original time of the Earth's formation. Soon after 4.5 billion years time, right? The first differentiation. So that bulk silicate part, because we are dealing with silicates, we are not dealing with much on metals. We are dealing with silicate. So original amounts of or the original mass at that time prevailing was the silicate portion. There everything was together, right? There was no mantle and core separately, right? Later on, the second stage of differentiation caused this second layer, the other layer, crust. Okay, either oceanic crust or either continental crust, whatever it is. We had crust formation as a result of some melting, again some melting, right? So now what we have is a mantle we have, a crust we have, and a core we have. Okay, but at the original situation, the silicate portion we consider as the primordial parent material for us, for our planet, right? Of course, the metal part was there, that was concentrated in the core, right? So that original composition, the primordial composition, the silicate portion is considered as the bulk silicate earth, right? Bulk silicate earth, or the primitive mantle, right? The primitive mantle at that time, because it was the primitive type of the mantle where just started, the continental crust formation just started, right? So that is a primitive time, or the primordial time. That is a formation time. Okay, so that composition we term as bulk silicate earth, BSE composition, and that BSE composition is lying here. So you can see this rectangle here. Okay, this composition, the strontium isotopic composition, and the neodymium isotopic composition is here, right? 0.5126 something, a little bit, 267 or something like that. Okay, and for strontium isotopic composition, it's falling somewhere here, right? That's the primordial composition of isotopic value for the primitive mantle, right? So that is sometimes we term it as bulk earth also, bulk earth. So that is one reservoir that we have to consider. That is the original reservoir actually. That's the original reservoir from which only we had now depleted mantle and other EM and everything, crustal, lower crust, upper crust, everything is formed after that. So we consider this primitive mantle as the primary reservoir, primary uniform reservoir. We consider it as a uniform reservoir because there was no crust formed at that time. So everything was together, silicate portion was together, right? So uniform means silicate composition was there together, right? That's why. So that is one of the reservoirs, one of the primitive reservoirs. Out of that only, we had this every reservoir form. Now we don't have a bulk silicate earth actually, right? You know, now everything is evolved, but remember the composition similar to the bulk silicate earth is still prevailing, right? We will see where those areas, right? So that's one reservoir, and this reflects, as I mentioned already, this reflects the isotopic signature. Isotopic signature of what? The primitive mantle. The isotopic signature of the primitive mantle, as it would evolve to present day without any subsequent fractionation. That means if we consider in a diagram, right, in a strontium and neodymium isotope diagram, because these are not elemental diagrams, right? These are isotopic diagrams. So if we had some composition, initially, it will evolve, right, to the present day value, right, to some value in the present day. So right, it will evolve like this, right? So that means strontium value is also changing, neodymium value is also changing, right? So overall evolution is something like this. Okay, so if we had this composition without any disturbances means the other processes, later processes. For example, at that time we mentioned that there has been no crust formed, right? It was just the mantle only, the core only, right? It was just only the core. So if it was there as it is without any disturbance, that means the BSC, if it was there as it is, it will evolve like this. It will evolve like this. But now what has happened is it has been disturbed, right? It has been disturbed by various processes. So this BSC evolution has deviated in different directions, right? In different directions. So that's why we have different reservoirs in different regions in the mantle. So you see here, so different reservoirs you can see here that indicates this evolution has been disturbed. Okay, this evolution has been disturbed. So anyway, if it was there as it is without disturbance or fractionation, disturbance means fractionation. That means exchanging of isotopic or elemental compositions here and there. Right? That is in simple terms fractionation. In other words, you can consider it as depleted or enriched, right? So once one reservoir is get depleted, the complementary reservoir to it will get enriched. For example, we talked about partial melting, right? We talked about partial melting where the melt is produced. The melt is produced at the same time. What happens? The original part becomes the residue, right? You have the melt. So when the residue becomes depleted, what happens to the melt? Melt becomes enriched, right? So the melt is the complementary part to the residue. So when the residue get depleted, melt becomes enriched. Okay. So being enriched or depleted is the disturbance to the evolution of the bulk silicate. So if it is depleted, then it will move or deflect. Its direction gets deflected. Okay. So it will get changed its evolution direction. But as I mentioned, some samples from oceanic basalts, right? Some oceanic basalts have this isotopic signature. So this isotopic signature means equal to the bulk silicate earth. As we know, the bulk silicate earth should be no longer, because now the earth has differentiated. But still, we have some oceanic basalts. That means some basalts we encounter from some oceans still contains some isotopic signature, which is very common, very close to the bulk silicate earth values, right? So that's why you see here this some blue areas. Here you can see some blue areas. Can you see these blue areas? Yeah, these blue areas, you see here blue areas, they are coincident, and also this yellow area, orange, whatever the color, right? This area is coincident with the BSC composition, BSC value, bulk silicate earth value, right? So that indicates there should be some regions in the earth still analogous to the bulk silicate earth composition, right? So we will see these things also later on, but just keep in mind, right? So that is one of the reservoirs, the first reservoir that we have to introduce, the bulk silicate earth. And the second reservoir that I have already mentioned that too, which is the depleted mantle, right? So the depleted mantle, which we take as the second reservoir. Okay. Right. So the DM, depleted mantle. So I mentioned in the strontium neodymium isotopic diagram, this depleted mantle comes over here. That indicates high neodymium values, and low strontium values. Okay. Low strontium values, right? High neodymium values and low strontium values. High values of neodymium and low values of strontium. Okay. Right. So that is the characteristic of the depleted mantle. So you know This is where this is located, mostly beneath the mid-ocean ridges, right? Mostly beneath the mid-ocean ridges, or the upper mantle, actually, the region of the upper mantle in this part. So in this region, you have the depleted mantle. Actually, you can't make it as a boundary because the entire melting is taking place in this region. So all this area, you must have a residue, right? So that is the depleted mantle. So this mantle is having high neodymium values. What is the reason? Because by now, I think when you learned about the neodymium isotopic systematics, isotopic composition, or the isotopic system, you may have learned it. Last time also, last week also, I reminded you about the incompatibility of the elements, right? What is the system to produce strontium and neodymium? What's the difference? The parent isotope for strontium and neodymium we have. So neodymium is produced by what? Samarium, right? Strontium is produced by what? Rubidium, right? So the behavior of rubidium and strontium are opposite, right? Did you understand that? Behavior of rubidium and strontium, rubidium and samarium are different. Rubidium is highly incompatible. Okay, rubidium is highly incompatible, meaning it readily incorporates into the melt. So the more you melt, the more rubidium will be escaping from your sample. Okay, but samarium is opposite. Samarium is highly relatively compatible. Relatively compatible. That means it that likes to stay in the residue. Okay, that likes to stay in the residue. So then what happens after melting? If you measure the compositions in the residue, what you will get mostly samarium should be there in big quantities. But if you measure the rubidium in the residue, you will get a small value, low value, because it has already gone with the melt, because it likes melt. It's highly incompatible. So if you measure the mantle sample from the depleted mantle region, okay, from a depleted mantle region, that means if you measure isotopic composition from a sample from here, right? If you take a sample from here and measure the isotopic composition, so elemental composition first you measure. What happens? Samarium. Since samarium likes the residue, there should be huge amount of samarium, right? What about rubidium? Since rubidium likes melt, okay, because it's highly incompatible, the rubidium should be less in the mantle, in the residue. Why? Rubidium should have incorporated into melt already. So therefore, rubidium amount should be low. So what does this mean? If you have very high amount of samarium, right? If you have very high amount of samarium, as a result of decay, as a result of radiogenic decay, the more you have the parent isotopes, the more you have the daughter isotopes as well. Daughter means neodymium, right? Samarium produces neodymium. The more you have parent atoms, the more you will result daughter atoms also, right? So you will have with time, you will have high neodymium atoms produced as a result of lot of samarium parent isotopes. But in the case of rubidium, in the residue, you have limited amount of rubidium. That means less amount of rubidium. So therefore, the isotopic decay over the time produces less amount of strontium isotopes. Is it clear? Because you have less number of rubidium atoms, that means less number of parent isotope. So you will definitely should get less number of strontium or daughter product. So this is for the same sample, okay? This is for the same mantle sample. So in the mantle, that means in the depleted mantle region, if you take a sample and measure neodymium isotopes, because now it has taken some time, right? So therefore, radiogenic decay has taken place. So you will have high neodymium isotopic value, neodymium ratio, neodymium value, whereas you will have low strontium value because less parent atoms are there. Therefore, you are always getting a low value of strontium. Okay, so that's the reason why you have low strontium isotopic composition and high strontium, high neodymium isotopic value for the depleted mantle. Do you understand that? Did you get the point clearly?
Yes.
Yeah. So that is the principle. So that's the concept you have to understand. Okay. So for other SOS also the same concept is there. Depending actually the the daughter isotopes are proportional to the parent isotopes. So that is the principle. Right. So considering that, you have to understand the compositions of these reservoirs. So DM is the best example to demonstrate that concept and also the phenomena, the radiogenic decay, where you can easily reflect these isotopic values in different proportions, right? All the geochemical properties also matter. That means the compatibility or the incompatibility matters for this isotopic characterization. Okay, right. So the depleted mantle is having a characteristic high neodymium isotopes and low strontium isotopes. So that is the second reservoir that we consider. So one more point is there, that is the this depleted mantle is the source for mid-ocean ridge basalts. Okay, mid-ocean ridge basalts. Why we used NMOB? NMOB means normal mob. Okay, because the mob is also characterized or categorized into two sections, right? E mob, actually not two, three. E mob, D mob, and N mob. Okay, the majority of the mob is N mob. Majority of the mob is N mob, but some compositions are there E mob, and some compositions are there as D mob. Actually, it's a kind of small difference there in terms of isotopic compositions, where you see here a bigger diagram, right? The mob composition is all these isotopic area, this blue region, this black region, okay, sorry, green region represents the mob composition, mid-ocean ridge basalt composition. Actually, it's very difficult to show in this diagram the mob composition, but it lies in between this region. Okay, the mob composition. So you can see the mob composition if you take this as the mob. Okay, it's not marked there, but if you take this region, this square, or it's actually not a square, but it's something like what do you call this, ellipse, right? Like an ellipse, right? So it's like an ellipse, like this, something like this. So this is the mob composition. Okay, so in this mob, unlike the DM or BSC, this is very broad. This is very broad. So you have two ends. One end is here and the other end is there, right? So if we have, for example, in the DM, depleted mantle, so we recognize that depleted mantle is having high neodymium values, whereas low strontium values, right? High neodymium values and low strontium values. So this is the characteristics of depleted sample. Depleted means it should be high neodymium, it should be low strontium, right? That is the nature of the depleted sample. Right? If you are talking about a depleted sample, either from wherever it is, right? If you are getting a high neodymium value and low strontium value, both should be there to say that it is a depleted value, depleted sample. So for the MOB also, you have two ends as I mentioned, and one end here you can consider as having high neodymium and also low strontium, right? This end. So that means this end is depleted. So that part you can term as DMOB. So the MOB composition which is more or less lying in this part, that means towards the high neodymium values and low strontium values, is called the DMOB. And the opposite part, that means here where you have low strontium values but low neodymium values but high strontium values, that part is called enriched part. So EMOB is termed there, EMOB and DMOB. That's how the EMOB and DMOB define. So those two ends are EMOB and DMOB, and entire other region, that means the most of the area in between, is termed as the average composition, or in other words, NMOB, normal MOB. Okay, so that's how the MOB is also divided. But anyway, the MOB is a very broad composition. It's lying in this way. So therefore, you can consider it has two ends also, right? DMOB and EMOB. Anyway, so the depleted mantle here, which is directly correspondent to the NMOB. Okay, this depleted mantle is directly complementary to the normal MOB. Okay, so that means if you take the normal MOB composition somewhere here, if you melt this sample, if you melt this mantle sample, you will end up with the depleted depleted mantle as the residue and MOB as the product of the melt. So if you have a mantle, you start melting and you produce a melt, right? You produce a melt, and you are remaining, you are coming, or you are left out with the residue as well, right? You have a melt produced, and you are now remaining with the residue. This is the original mantle that you melted. So from this one, if you can produce the MOB composition, right? Suppose you produce the MOB composition from this mantle, and definitely the residue you are getting is equivalent to the composition of the depleted mantle. Okay, so MOB is complementary to the depleted mantle. Okay, so that's why sometimes we call the source for the MOB is depleted mantle. Okay, source for the MOB is depleted mantle, right? So this is the concept. Anyway, the depleted mantle and MOB are complementary to each other, right? So this difference comes only because of the compatibility and incompatibility nature. Neodymium is high in the residue, and strontium is low, right? Strontium is low, or in other words, strontium is high in the melt. So that's why this MOB has high strontium compared to the depleted mantle value. Okay, so this difference is there in strontium, and also this difference is there in neodymium. Okay, so this is the concept behind the depleted mantle and the MOB. They are complementary to each other. So anyway, the point you have to take home is strontium and neodymium difference, okay, in depleted mantle and MOB. Okay, so these are some other reservoirs that we have to consider. And the other one, another one is there, the enriched mantle source. The enriched mantle source we have to consider. Okay, so I think before moving into the enriched mantle today, because it takes a little bit longer, so I want to just summarize the today's discussion before moving to the enriched mantle region, because we have to very carefully understand this concept, right? Otherwise it's very difficult to grab the mixing models, because we are going for a mixing concept later on, because as I mentioned, this geochemistry, in geochemistry we use these reservoirs for mixing calculations also, right? Mixing models, right? So therefore these reservoirs are very important, because one reservoir, suppose you have one reservoir here and another reservoir there, right? We can calculate the mixing in between these two reservoirs. So if you have a sample which is lying somewhere here, another sample which is lying somewhere there, okay, you can consider geochemically these samples which are available here are products of mixing between 1 and 2, right? Some proportion from 1 and some proportion from 2. These calculations can be done. This modeling can be done. So we call them binary modeling. Okay, binary modeling. And the samples which are lying here cannot be explained by this binary modeling. So if you had another reservoir, that means 3, number 3 here, then you can easily explain this behavior also. So this is called ternary modeling, ternary modeling or ternary mixing calculations. So binary mixing and ternary mixing is very important, because with that only we can understand some geochemical behavior of some samples. So I will show you some examples, applications, but you are not going to do any calculations, because at this bachelor's degree level, you are not doing this mixing calculations. Okay, if you happen to go for higher education, higher degrees, you will in petrology or in related fields in geochemistry, definitely you will have to do some mixing modelings. Okay, so but anyway, you have to be very careful in understanding these the reservoirs, because those are very important in calculations, right? Anyway, now so far we have been talking about the MOB, right? MOB and depleted mantle and bulk silicate earth. So where should this bulk silicate earth lie? Here you can see bulk silicate earth. The label is here. Okay, label is here. The bulk silicate earth label is here. At the same time, you have a question mark also. Did you see that? Question mark is here, right? So that means we don't know whether really there is bulk silicate earth remaining there. Right, as I mentioned, bulk silicate earth is the composition of the primordial earth composition, right? It's bulk silicate earth composition, primordial composition, initial composition. So now the earth has been evolved, as we know, crust and mantle evolution is there. So whether still BSc portion is remaining or not is uncertain. Why we can't investigate that much? Because we have very limited access to our mantle. Not only the mantle, to the Earth's interior, right? We have still the access only to this region, right? To the upper mantle only. Mainly we have upper mantle abundant samples. We have a lot of MOB samples, right? Coming from the upper mantle. Lot of OIB samples coming from, non-plume OIBs. So that those are also very close to the upper mantle region, right? Although a little bit deeper than the MOB, but still within the upper part of the mantle. But only plumes are bringing us the lower mantle samples. Lower mantle samples are brought by plumes, but you know the plumes are very rare. every 400 million years time, you get a one flow. Okay, so that is very rare, but mobs are every time, every minute you get mob magma, every minute, right? Not like the OIBs. So therefore, we have very, very limited access to the oceanic, the deep mantle basalt. So therefore, we don't know much about the composition of this, the lower part of the mantle. So lower mantle composition, we don't know much. Okay, lower mantle composition, we don't know much because we have no samples from there, right? So even this more OIB is coming, those are the melting products from this region of the lower mantle. They are not direct samples of lower mantle because they are not bringing the pieces of lower mantle up like this, right? No, they are not coming like that. They are just melted portions only. Like the depleted mantle melted portions are coming as mob. Mob is not really the mantle sample, right? It's a indirect sample from the mantle as a melt product only we are getting. DM is the direct product of the mantle, right? So lower mantle is not coming as sample. So we don't know the real composition of the lower mantle. Some indirect evidence we have from OIBs, but not the real samples. But as I mentioned before, in the diagram here, the lower mantle, the bulk silicate earth, composition coincides with some basalt composition. So this is one of the OIB compositions, one of the OIBs here, right? You see very limited OIBs are coinciding with the bulk silicate earth composition. This is also OIB, right? But it is not much coinciding, but partly coinciding. This is also partly coinciding, but anyway, only a restricted portion is coinciding with the bulk silicate earth. So what is the implication of that? The implication is that the bulk silicate earth can be equivalent to some of the OIBs. Some of the OIBs are equal to bulk silicate earth. Some, not all. Some of the OIBs are equivalent to bulk silicate earth, means some OIBs are probably products of melting of the bulk silicate earth reservoir, which is available intact in the lower mantle region. So available intact means it is there as it is. We have to suspect like that, right? So some of the portion of the bulk silicate earth is still remaining in the lower mantle region. Okay, so that implication is there, right? So in other words, some of the lower mantle, some regions of the lower mantle is equivalent to the bulk silicate earth. Okay, so that is the implication. So we have to think, we have to just arbitrarily put the bulk silicate earth into the lower mantle section because some of the OIBs are having the bulk silicate earth composition. So therefore, we don't know exactly where that is located. So therefore, we still put a question mark. You can just put a question mark because the location is uncertain, right? We don't know exactly. So that is the story behind the bulk silicate. Okay, so these are the main reservoirs that we have to talk about. But in the next class, I will be taking up the other reservoirs like enriched mantle and the other reservoirs that you are seeing here, right? Some other reservoirs are also there. Still, we don't know their locations as well, right? So we will consider them later on in the next classes, right? So maybe with this point today, we can stop the class here.